Daniel, can you use your mic?
Sure.
Okay, thank you. So can also use the mic. All right. Welcome, everybody. So yeah, I will jump between writing and the chat, but feel free to use the mic at any moment. Okay, so welcome to APM 462, nonlinear optimization. I wanted to start with famous optimization problem from Howard Gates, the stochastic gradient in neural nets. So if you heard anything about neural networks, the main mathematical basis behind it is just the gradient descent problem, the optimization problem. So if you want to know whether a cat is a cat, you have to take the yeah. Okay, so the stuff we do are very, very relevant for this type of things, data analysis, statistics. And yeah, like, if we go, I will keep showing some numerical examples of gradient descent. By the end of the course, I hope that you know how to do gradient descent mathematically and manually. You won't be tested on manual, all right, so let's go over the syllabus. So we can have 11 quizzes each week, and they're going to be about 20 minutes. So 1-2 questions taken from the suggested problems. I already posted 3 questions for next week from multivariable questions. And we're going to drop the worst 2. Okay, so you do 11, and we drop the this 2 goes to infinity. That doesn't make it. This 2 for 2. Well, I mean, I posted the suggested problems. Yeah, there's 3 questions, and I will take whatever techniques you use in those problems and make some questions. Oh yeah, perfect. Good taste. Okay, can you now hear me?
Prof?
Yes, can you hear me?
Yeah, I think like if possible, could you probably speak closer to the mic? Because when you get further away, we really can't hear.
Can you hear me now?
Yes, we can.
I will sit right here.
All right, thank you so much.
Okay. All right. Good, thank you. So, yes, we're going to keep 9 out of 11, just too loud. And 20-25 minutes, and the first one will be next week. Okay, so any question about quizzes? If you have a question, just let me know. We're going to have 2 midterms online in June and end of July. Okay, end of June and end of July. Again, the questions will be taken from the suggested problems, so I'll play with them and then put them there. Okay. And we can have a final assessment in August, which will be in person. It's during the end of the tutorial, yes, the last 20-25 minutes. Okay? Abhirani? Okay, good. What else? Oh yeah, and we also have 2 bonus presentations. So that's basically covering 6%, so like about 2 quizzes. And you just have to do either one of them or both or neither. So 50 minutes each, and just pick a topic, an application topic. I give you a list in the syllabus. Yes. If you do one presentation, so the question is, should he do? No, it's one presentation each. So 2 presentations, then it will be 3. You can do both, you get 6. You can do one, like in June, or maybe you're too busy in June and you do the one in August, you're going to get 3%. Yeah, is that okay? And I just have to see your face. That's the main. So don't wear a mask. I have to see. So if you make any mistakes in your quizzes and midterms, keep up, post them on Piazza, talk to me. For regrades, I have no deadline. Okay, so you make a private post on Piazza with your grade scope, and we will talk about it. If you don't know why Etienne removed some marks, again, come on Piazza, ask why. You won't be punished. We will not remove marks. Let me say that. We want you to find mistakes and understand them. So if you submit regrade, we will not remove marks. I know some people do it. I will not do it. Okay? Because I know in some courses, if you submit a regrade, you can go down. So that won't happen. Okay? Yes, each presentation is 50 minutes long. And you can just record it and put it on Piazza. So you don't have to do it in front of people. Just on your own, you go with your tablet, we see your face, and that's it. Yeah, make sure you participate on Piazza. So, because it's hard to work in groups. And yeah, make sure you get feedback on the suggested problems. So each week I will update the calendar with the problems, and make sure you do them and talk with your classmates, and also come on Piazza. Say I'm stuck on this step. Can somebody help me? And we will help you. All right. So is there any administrative thing before I move on to overview? So any administrative questions? Office hours would be online because the course needs to be online. But I can be after class. We can like do both synchronous. We can do what we're doing right now. So it can be both, yes. Any administrative questions? So what we are going to do, weeks 1-4 is basically 237. So we will do a multivariable optimization. So we have a Hessian and we find critical points and we classify them. So this is just a review, really, the first 4 weeks. Lagrange multipliers, if you remember them. So that's basically weeks 1-4, and it spills into week 5. Then we start talking about constraint problems. So we have Lagrange multipliers, Kantaka conditions on the Hessian. And then we sort of change material in weeks 9-11. Here we can have convex constraints. So our domain needs to be convex, our function needs to be convex. And the reason we need convexity is because the Hessian, which we will talk about, is positive definite. So all the stuff we did weeks 1-6, we will almost get them for convex functions, if that makes sense. So we will do a sort of Taylor expansion. These are words that we can explain. And whatever we did weeks 1-6, we will get them for convex functions. So I'm just giving you the rough idea. And finally, we're going to do calculus of variations. This one I will have, once we get there, I'll explain. So, yeah, so this is a little bit for, but the point is, instead of having our n vectors, now we are infinite dimensional things. So we're optimizing over functions. So if anybody took PDEs, differential equations, this is one of the topics there. So yes, we'll come back. Okay. Oh, you've studied it? In which course? Right. So you remember the name Dirichlet energy? Yeah, this is exactly it. So, but yeah, we will come back. Yes. I mean, yeah, that would be our first example. All right, just a small exercise to prove that it's easier to remember when you participate. So here's a list, and try to memorize some of these words. Okay, without writing them. So here's a list, and try to memorize pairs. Okay, so one word. Chips, salt. Okay. So I'll give you a few seconds. All right, so now what a distraction slide. So the difference between machine learning and neural nets, if you know anything about this, is that in deep learning, you don't need a human to label cat, dog, cat, dog, cat, dog. The AI can figure out what's cat, what's dog. Right, so you don't need to label. It's called unsupervised learning. Okay, so that's the distraction. So, can you tell me from this list which of these pairs do you remember better? So you have 2 lists of pairs. Which ones do you remember better? So, A or B? Huh? Sorry? Well, it's supposed to be B. So did you get it? Can you tell me on Zoom? It B, right? I hope so. Otherwise, it's a failed experiment. Anyways, I think you get the point that your brain automatically did work to fill in the gaps, bottle, lyrics, shoe, book. And just by doing this little amount of work, you memorize it. So that's the lesson. Maybe you worked hard starting from A, you weren't like, I don't know. But yeah, most people get B because you have to work. So it stays in mind. Oh, I see. All right. All right. So yes, this week we will be reviewing second year stuff. So 235, 237, whatever you took. I will redo most of the proofs that we need for this course. This is not a computation heavy course. The most you will need to do is compute derivatives, eigenvalues, determinants. So that's the main thing. Okay, so yeah, so let me start with a review. Yeah, all right. So first, what is a function called CK? So a function CK has k derivatives, and its kth derivative is continuous. A very easy example is f of x equal e to the x. Okay, because if you take k derivatives, what do you get? Yeah, which is continuous. So e to the x is in ck. In fact, it is in c infinity, right? Because you can keep taking the. Okay. All right. So now we start from first year calculus. I'm going to prove to you the mean value, right? So that we have it in our head, because this is really the foundation for the whole course. So take a C1 function, meaning that f is differentiable and f prime is continuous. By the way, the slides are online. Okay, so here's the result. This is called the slope of the secant. I have a picture I will show you next. The result is that if you give me any a, b, I can find you some c so that f prime of c will equal the slope. Okay, that was mean value theorem. So I'm going to show you the picture. This is more intuitive. So this gray line is called the secant, and it has a slope fb minus fa over b minus a. And it says that, so the blue line is your function, and it says that there exists a point where there exists a line that will be parallel to the secant, and this line will be tangent to the graph. Okay, so again, this is called secant, and mean value theorem says, which we can prove, that there exists a tangent line. With the same slope. Call it theta. Okay, so this angle is theta, and this angle is theta. Is that okay? So it says you can move your secant and eventually you hit your graph. Is that okay? Zoom people? Can I get a okay? Not okay? Because I don't know if you're hearing me. Hello? Can you hear me? Can you hear me? Okay, great. Yes, all right. Thank you. Yes, perfect. Thank you. I have to check. You don't die on me. All right, so let me prove the invalid here. Here's a nice example. So I will do it on the side. So again, we have cosine of x minus cosine of y over x minus y is equal to cosine prime evaluated at x equal c for some c in xy. Okay. What is the derivative of cosine? Minus sign. So this is minus sine of c. Okay. So here's a nice result. What do you know about the upper bounds of sine? What is it bounded above and below? Yeah. So then we have that cosine of x minus cosine of y is equal to x minus y sine c. So it's less than x minus y. Okay. So this is how we're going to use the mean value theorem in this course. We're going to have a function and we want to find this modulus, and we use the mean value theorem and bounds on the derivative of the function to get a growth on the function. So in this case, it tells us that the difference of cosine grows at most x minus y. Is that okay? If the what? Yeah, so the question is, what if the function has a derivative, but it is unbounded? Then the function will not be C1. And, well, okay, so wait. No, here's an example that works perfectly. So here's EX minus EY, right? What is that equal to? What's the derivative of a to the x? Yeah, it's the same, right? So you have e to the c, and exactly, this blows up. So you don't always have it. Yeah, absolutely. But here's the thing, though. C is in xy, right? And e to the c is bounded by what? E to the y. So when your domain is compact, your derivative is forced to be bounded. So we're gonna, I don't think, yeah, we'll prove this. This is called extreme value theorem. So let me write it here as well. But we're gonna review all these things. So if G is continuous in AB, then you have that G of X is less than some M and little m, okay? And it actually attains it. So C1, C2. Okay, so yeah, that's the result we need. Any question, Zoom? You can ask. I move on? Right, so yeah, that's how we're going to use mean value theorem. So let me review the proof. So you have to use this auxiliary function, g of x, okay? And this is how we define it. So f of x, and then these are constants, they don't depend on x. And there's an x over here. Why is this interesting? Because if you remember a little bit, Rolle's theorem. So in Rolle's theorem, we needed, I'm going to reprove Rolle's theorem, but I'm just saying, we needed the function to come back to itself. So this function does the following. It does something crazy, and then it comes back to 0. Okay, so it does something like this, and then it comes back, and we're going to prove that there exists a peak. So there exists a peak, and you can put a tangent line on it. Okay, so that's the intuition. Okay. And then, right, so g prime of x, you have f prime of x, f of a dies out, derivatives of constants are 0, and derivative of x minus a is 1. So to prove you the result, I just have to show you that there exists some c, so that g prime of c is 0. Why is that? Because then you get f prime of c minus f of b minus f of a over b minus a is 0. Right? So then f prime of c is equal to the slope of the secant. Okay. If you have a question, Zoom, you can tell me. All right. So I'm basically reproving Rolle's theorem for you. So here's the trick. So in Rolle's theorem, you can assume that your function attains a maximum inside AB. So here's the picture. So here's A, and here's B. And we can assume that there's an interior point where the function attains a global maximum over here. So let me explain why. So suppose that both min and max are attained at the endpoints. Okay. So suppose that the maximum, so m is equal to g of a, which is equal to g of b. Right? But these are both equal to 0. Right? So, and yeah, suppose the min is also attained there. So min and max. So you get that min is 0 and the max is 0. So you get that g of x is identically 0. In which case, the derivative is always 0. Right? So g prime, we're trying to prove that there exists a c, so that g prime of c is 0. But g is constant, and the derivatives of constants are 0. Yeah. Okay. So I can assume that my m happens inside. Is that okay? So that's the main trick. So let's see, why does it imply it? So since it is a maximum, this value C, you have the following picture. When you're coming from the right over here, so this is G C plus epsilon. This is less than the maximum. So this guy is negative. Okay. When you're coming from the left, GC minus epsilon, you will be, yeah, so this will be again, how do I say it here? So here, I think this is a small typo. Let me fix it. It's minus epsilon, like this. Okay, sorry, I will fix it. Okay. All right, and then you learned that the definition of the derivative G prime at C is equal to the limit of epsilon as it goes to 0 from both left and right. So that's the main reason. And you have, let me write the first one. And the first one is less than 0, and the other one is bigger than 0. So G will have to be 0. Okay, that's the trick. That's all there is. So this is the entire proof of mean value theorem, completely self-contained. Okay, because usually you have to prove Rawls theorem, Fermat's theorem. I put them all in one slide, so you don't have to go back. Any questions, Zoom people? If you have a question, just let me know. All right. So let's review Taylor's theorem, Taylor approximation. Again, you want your function to be continuously differentiable, C1. And then you have the following formula. So this one says, suppose this is your function G, and you have Gx plus H, and this is Gx. It says that if you want to approximate Gx plus H, you can just use the line with the slope G prime of X. Okay, so let me make it like this. So this is called linear approximation. So if you Google Taylor's theorem and it doesn't show up, just Google linear approximation to your function. Okay, so let me repeat. The way you use Taylor's theorem, actually, I will show you the example. So here's an example. I want to figure out how cosine behaves close to x. In fact, forget x. Let me put x equals 0. So you have cosine of h. And what is cosine of x out of 0? 1. And then minus h. What is the sine of x? The sine of 0, sorry. Yeah, 0. So Taylor's theorem tells you that cosine of h as h goes to 0 is linearly close to 1. Okay, so this is the speed it converges to 1, right? So, which is pretty cool. It tells you how fast it goes to 0. Can I make it faster? Yeah, I'm gonna spread my. But yeah, I can make it faster if I put cosine x squared. That's fine. All right, questions? Okay. Yeah, so this little O means that it grows faster, it goes to 0 faster than h. So this OH, so what's an example of an OH? What's an easy function that will go to 0 if you divide by h? Just the simplest possible. Yeah, h squared, that's it. Then you have OH, h, h squared h, and limit of h, which is 0. So it tells you that at least you go linearly fast, but you could be going like exponentially fast, or like h squared fast. Good question. Because yeah, it doesn't really tell you how fast. For that, you need mid-value remainders, which we will talk about. All right, so we're gonna do this like 5 more times. I'm gonna prove a mean value theorem and then prove the Taylor theorem for it. I'm gonna do it for second order, multivariable, first order, and then multivariable second order. Okay. So this is the left-hand side in Taylor's theorem, right? Yeah, so this is the left-hand side in Taylor's theorem. And I want to show that the guy on top, I want to show that this goes to 0. That's all. I want to show that it goes OH to 0. Okay. Good. First, you apply mean value theorem over here. Okay, so mean value theorem said that you can write the slope. So let me say how we apply mean value theorem. This guy divided by h is equal to g prime of, we can call it c. Let me write it like this. Same thing. And so you rearrange. Right. Okay, now I'm in good business because I can factor out h. Okay. So you take out the h and they cancel out. So this was h over h. Right? But then this guy is equal to 0. So let's go to the last step. So the very last important is because we assume that G is C1. So G prime is continuous. And so this guy over here is equal to G prime of X. So they cancel out. Okay, so continuity, in case you don't remember, it means exactly this, that you can swap limit and function. You can bring in the limit. So let me do it on the side because it's not complicated. So continuity says the following, that limit of h going to 0 is equal to g prime of the limit. But this is just g prime x plus theta 0, which is g prime x. Is that okay? Just reviewing. Yes, can you back 2 slides where you explain how NVT works in this proof? Yes. So so you see, this is what you have on the left-hand side of Taylor's theorem. And then mean value theorem tells you that the secant slope is equal to g prime of x plus theta h for some theta. This one we called it C. It's the same thing because you can solve for it. So you have C minus x over h. So you can use either form. You can either use g prime c, or you can use x plus theta h. Okay, for your mean value, whatever you find more comfortable. I'm not sure which one you've seen. I think you've seen g prime c, right? Okay, so yeah, so let me explain again. Then, so yeah, we know that this guy is equal to g prime c for some c in x plus h, right? But then what is this interval? An arbitrary value in between would be of the form x plus theta h, where theta goes from 0 to 1. Is that okay? So C will fall somewhere in here. Is that okay? Abhigrami, is that okay? All right, so we use continuity and that proved that is limit 0. So that means the top is equal to some guy OH. We don't know what OH is, it could be H squared, like somebody said. So we just know that it goes to 0 faster than H. Okay? So this is called Taylor approximation. All right. I know the proofs will be very repetitive, but hopefully you get the idea. So we can further expand Taylor's theorem, and that would be the most we will do in this course, will be second order. Okay, so we won't go further than second derivatives. That will be the end. All right, so this is the mean value theorem for second order. So it says that you can find some, call it C, if you like, in x plus h, so that you have this formula in terms of the derivative as well. Okay. And then nobody really uses mean value theorem in this form. Most people use the one I just showed you before. So this one really only serves the purpose of proving Taylor's theorem up to second order. Okay, so think about it as a lemma. Right, let's do an example. So take square root x. And what do? We plug in x plus h, x. We take one derivative of square root x, which is equal to a half square root x, right? And then we take second derivative of square root x. Which gives you minus 1/4 x to the 1 plus a half, which is 3/2. It's probably a typo here. Should be 8. I'll fix it. Okay, so this is the second order approximation of square root x. Can someone tell me what happens when x is 0? Well, you can only take x to 0. So yeah, what happens at x equals 0? It doesn't work, right? Right. So that's what I say. But at least you know how quickly you diverge. So this is the power of Taylor approximation, that you know it doesn't exist, but at least it tells you how fast you blow up. And you blow up as a square root. So another application of this stuff is, I mean, we will do a little bit of PDEs where you have blow up of solutions, and this is really the bread and butter. Okay. All right. Any questions? So let's prove second order, then we'll take a break. Here you have to consider this crazy long function. You don't have to learn any of this. So this is just to understand the argument. Again, this is because of Rolle's theorem. So I just want you to know the main idea, not the specific example. I want you to know how the proof goes for this. So this function is very interesting because it has 2 zeros. So if you're going to draw the function, it hits 0 at minus h, at 0, and at h. Okay? Any guesses on what you can get for G prime? What's the implication of the derivative? By Rolle's theorem? What does Rolle's theorem says for G prime? So you have, huh? How many? At least how many? Yeah, at least 2. Like you can tell, because I can make, there would be at least 2 zeros. And that's because Rolle's theorem, let me remind you Rolle's theorem, which we proved. It says that if f of a is equal to f of b equal to 0, then there exists C in AB such that f prime of C is 0. Okay, but here we have 2 of them. So all right. Okay, so then we have 2 of them. We have a C1 and a C2. So that in this picture that we just drew, here's the C1 and here's the C2. Okay, so you hit in these places you have G prime of C1 is 0. And now you play the game again. You have two zeros. What can you say by Rolle's theorem for G double prime? Yeah, you will have at least 1 0, right? Yeah. So by applying Rolle's theorem again to G prime, we have a C3, so the G double prime is 0. Okay, and that will be our mean value in the second order mean value theorem. Yeah. And you can keep doing this. So if you want to get third order, fourth order, you will have, you know, at least 6 zeros, then 5. How does it go? You lose, yeah, you lose 1 each time. 6, 5, 4, 3, 2, 1. Okay. Any questions, Zoom? If you have a question, let me know. All right, so that was the main trick. Okay, but we don't really use the mean value theorem. We only are going to use it for Taylor's theorem. So this is what we are interested in. We're going to show that locally I can approximate by a polynomial. Okay, so let me show you the example. So let's do the same one. So cosine x equals 0, and cosine at 0, which was 1, h prime minus sine at 0 plus a half h squared. What's the second derivative? What's the derivative of sine? Cosine. So you just have minus cosine, right? So double derivative of cosine is minus cosine, right? Yeah, at x equals 0, and then OH squared. All right, this guy is 1, sine of 0 is 0, cosine of 0 is 1. So you get minus a half h squared, and then you get OH squared. Okay, so what does it say? It says that you go to 0 at least h squared fast, like you guys said. So you actually go to 1 even faster than linear. You go h squared. So each time h goes from, I don't know, 100 to 1,000. Okay, cosine of h squared minus 1. Actually, this is a good example. Let me talk about it. So suppose you have h 100 and h 1,000. It says that cosine of h minus 1 will be less than 100 squared, and cosine of h tilde will be less than 1 over 1,000 squared. Okay, so every progress you make towards 0, you go even faster, quadratically fast. Okay, so this is an approximation result. So that tells you that the higher your Taylor series, the better approximation you have at the point where you expand. Okay. Questions? Zoom? All right. So the next one is multivariable, right? Yeah. So let me finish this Taylor so that next we're going to take a break and then do multivariable. All right. So the proof is short because we do the same trick. So this is the left-hand side in Taylor's theorem. Okay. So this was the left-hand side in Taylor's. There's no plus here. And on the first step, we apply second order mean value theorem. So let me explain. So the result we proved before was that if you take this guy divided by h squared, it will equal a half G double prime x plus theta h. Or if you like C, however you like it. This was the C3 that we found. Okay? Okay. All right. So we apply mean value here, and then luckily we can factor out the h squared. So we have G prime x plus theta h minus G double prime x. Okay. So let me go to the next step. So we, over here, we have an h squared on top and an h squared on the bottom, and they cancel out. Is that okay? And then we assume C2. So that means G double prime is continuous. So you can swap limit and function. So you have G double prime limit of x plus theta h, which is G double prime x. All right. So that proves that that the guy on top here decays like OH squared. And if you give me CK, I will prove you OHK. That's basically the game. Okay, so we're not going to use this, of course, but the more derivatives you give me, the better approximation I can do. Okay? All right, so let's take a small break and we'll start again in 10 minutes. How is it so far? Is it okay? Huh? Yes, it is. What do you guys think? Is it okay? Do you remember any of that? Uh, Did you do it? Okay. Right, right. Um, but like you took 235? Oh, 237. Okay, okay. Who was your prof? Arthur? I'm using the notes from Gerard. Oh, okay, good. Yeah, they're good ones, eh? Yeah, no, it will mostly be computation. Yeah, yeah, yeah. I mean, it will be like half and half. Like, we go over the method, but we have to prove you the method. But I mean, you won't see epsilon delta. That's what you. There won't be any epsilon deltas here. Sorry? Yeah, yeah. And I will upload this. Yeah, like I mean, we will do like second order tests, second order derivative tests. Uh, I mean, I will maybe mention, maybe, I don't know what you've seen, like classification of critical points, regular, non-degenerate. What are your programs, by the way? Like economics, major, math major, physics. Huh? Oh, statistics. Oh, nice, very nice. Some probability. Nice to meet you. What else? Oh, like I see. There's an APM sort of stream. Oh, I see. So, what about you? Math, physics. I was a specialist. I didn't took any applied courses. I wish I was like taking number theory and like, eventually, why don't you take a breath first? Oh yeah, in the summer, of course. Probably, what about you guys? Oh wow. So do you have to take a lot of what, like, is this like your last math course or? 466? What is that? Huh? Oh, that's fine with Seco. Oh, I heard this is mostly slides. Yeah, yeah, he'll like ask a lot. It's not very hard. There's no stochastic calculus. I don't know if you know stochastic calculus. There's no. It's truly because he has his own company. Maybe you get a job if you do well. Sigma Analytics. Yeah, I mean, there's a lot of, I don't know, I mean, applied people. You should check the grad courses. You can just audit. You don't have to take the course. Because there's applied courses. I mean, I don't know, but we have like biology, we have physics, like Siegel does quantum mechanics. There's a bunch of, yeah. All right. Now let's review second unit. So the picture you see here is a function and with a green fxy, and then this graded Mexican hat is the Taylor approximation. Okay, so this is a polynomial that approximates your f. Okay, so that's what happens in 2D. If you want to figure out what happens in 1D, just take a slice. So any slice of a Taylor approximation is a 1D Taylor approximation. Oh yes, right, that's right. Oh yeah, because they use the wavelengths. Yeah, excellent. All right, so now we have to go into gradients. Hopefully you remember a little bit. All right, let's start. So we need the Euclidean distance or Euclidean norm. So in 1D, you just take a difference of two numbers. In higher dimensions, if you want to compute, let's say V1, V2, like V and W, and you want to compute this distance, then it's given by V minus W. So you have V1 minus U1, Vn minus Un. Okay. So this is called the Euclidean distance. Right. V dot U is called Euclidean dot product. And pictorially, it says that if you give me a vector U and you give me a vector V, then this guy over here will be the length of this projection here will be given by VU. Okay. So this is a number. I should compute one for you now. So 1, 1 dotted with, I don't know, 1, 0 will equal 1 times 1 plus 1 times 0, which is 1. Okay. So you just multiply the coefficients, the components. Oh yeah, you took linear algebra. You should know this. I taught linear algebra. This is like projection operator. Oh yeah, you should know this. Yes. All right, good. What's the gradient? So the gradient of a function is the unique vector denoted as nabla f of x, and it satisfies this limit problem. Okay, but nobody uses this. The one we use is the one I'm going to write over here, namely that gradient of f is equal to the vector of the partial derivative. Okay, you can take either one as the definition, but then you have to prove the other one. So you can start however you like. Okay, take your definition, whichever one you prefer. But yeah, we won't really use the limit. We will use it for proofs. But when you actually compute things, please use the partial derivative. It's much easier. And I think I do a computation over here. So what do you think is the gradient of e to the x plus 2y? So let me do it here. Nabla of f. For this guy, what would be the first entry? Yeah, second one. Yeah, perfect. So let me explain why. So the first one is d dx, and the second one is d dy. Okay, and then the e to the y comes out, and the e to the x comes out. Okay. Okay. That's all. It's not. I know you've seen this. No, sure. All right. We also need a quantity called the directional derivative. So this is the rate of change in a certain direction. Now, when you're in one dimension, you only have one direction, so you don't really care. But in higher dimensions, you can change in depending on where you point to. So here's the definition. You can see a bunch of different notations. You can see it as dv f of x. You can see it as fv x. And I will do some computations because this is too many symbols. So the definition is that you start from x and you make a little bit of movement ahead in the direction of v. Okay. And so that's the definition. On the first step, you do chain rule. Okay. Or if you call like a total derivative, whatever you've seen. And that's how you get this step. And then you notice that this is just the dot product of the gradient with the vector v. So you can write it in short form as gradient of f dotted with v. Okay. All right. And if you're working in 2 dimensions, as we will most likely do for this course, you further have the formula, this formula here, which is the angle between the gradient of f and v. Okay. So let's do some Zoom people. You have a question? If you have a question, please let me know. Yeah, so there's some nice pictures when you do that stuff. So suppose this bump is your function, and you ask to find the rate of change along V or along U. One way to visualize it is you take a slice in the direction of the vector. So here, that's what you do. You take a slice along V, and you just compute a one-dimensional derivative, or along U, and you compute this derivative. Okay, so that's the intuition of directional derivative. You can translate it into a 1D problem. Gradient is not 1D. Okay? Gradient looks in all directions. Directional is directional, has one vector. Okay. All right, let's do some examples. So I'm going to find the directional derivative of this function at xy origin 0, 0. And I'm going to do it for each of these vectors. All right. So let's check the first one. So by definition, the directional derivative along the direction 0, 1 is given by the dot product of the gradient with the vector b. So let's find first the gradient at 0. So we talked about this. This was ex2y, 2 times ex2y. And you plug in 0, so you get what? What's the vector? Huh? Yeah. So then, oh yeah, right. So then you have, so then you dot 1, 2 with 0, 1. Okay? And that gives you 2. And hopefully you observe that this is nothing else but the rate of change along y. Okay, so let me explain it with this picture. So if one of these guys is y, so you need your vector to be 0, 1. So let me say it this way. If you want to find the partial derivative of f in the direction xi, take the gradient of f dotted with ei, where ei is the guy that has a 1 in the ith location. Okay? Does that make sense? Shall I prove it? That's because the partial of f is equal, the gradient of f is equal to partial derivatives. So when you dot with the ith standard vector, you extract the partial derivative, the ith partial. Okay? All right, good. I just want you to be able to move between directional derivative, gradient, and partial derivatives. So they're all different, but they're related. Okay. All right, so that's the first one. Let's do the second one. Now I want to find the directional derivative along 1, 2. Well, I already found the gradient of f. So then I dot with the normalized 1, 2. Okay. So what should I say here? Yeah, let me do the computation. So you have 1 times 1, 2 times 2. Yeah, it's wrong. Sorry. What do you, yeah, square root 5. Yes, thank you. No, it's square root 5. Yes. I'll fix it. Thank you. So then this guy is 5 over square root 5, which is square root 5. Yes, thank you. Okay. Anyways, yeah. That's the one. Oh yeah, and yes, no. And now this is equal to the norm of the gradient of f. Okay, so gradient of f is equal to 1 plus 2 squared, right? Which is equal to square root 5. So we'll come back to this, why this is interesting. This would be the maximal value of the directional derivative. So if you remember from the first slide, we have gradient descent. This is gradient ascent. The function has the maximal increase in the direction of the gradient. So you see this 1, 2 squared 5 is nothing else but gradient of f divided by its norm, right? 1, 2 squared 5. And we'll come back to this. Question, Zoom? Another one that's very interesting is to take the direction with minus 2, 1. This is interesting because it looks very familiar, right? It almost looks like 1, 2. And pictorially is as follows. So 1, 2 is like this, and minus 1, 2 is like this. So what do you know about uv equaling 0? What can you tell me about your angle? Huh? Yeah, perfect, thank you. And we will use this amazing result that gradients are normal to the level sets of the function. It will basically be a computation like this. Okay. We will use this a lot, so I will do it slowly when we get there. All right. Good. Now let's talk about why people care about the gradient. So if you give me a surface of f, and you compute the gradient like we just did, 1, 2 at the origin, it tells you how the function grows the maximus. So this is xy. And let's look at f of x ex plus 2y. So this always grows like this, and it grows like this. Okay, so is that okay? So the function, so this is the positive values, 1, 2, 3, 1, 2, 3, minus 3, minus 3. So the function increases, right? And we just computed the gradient of f at 0. It was 1, 2, which indeed points to the positive quadrant. So it tells you that your function grows when both x and y are positive. This is where you get the maximal growth. I'm going to prove this. I'm just doing the example. Okay? So how does it follow? We just have the following formula that dvf of x is equal to gradient of f dotted with v, and which is equal to this gradient of f norm times cosine of theta. And theta is the angle of the vector v. Okay. Can someone tell me for which theta cosine of theta is the biggest? Yeah. So when theta, I have it here. So when theta is 0, cosine theta is 1, which, going back to our picture, it means that gradient of f and v are parallel. Okay? So the maximal directional derivative happens when you move in the direction of the gradient. So we found that number 1, 2. It means e to the x to y grows the fastest in the direction of 1, 2. And if you want to talk about gradient descent, which is what people do in optimization, where you have the lowest, you have the most decrease, the fastest decrease. You look at when the directional derivative is the smallest, which is -1, right? The cosine of theta -1. And so pictorially, you're moving opposite to the gradient. So you move it the other way, okay? And this is called gradient descent. So when you want to do gradient descent, you take minus of gradient of f of x normal. So this is descent. When you want to find how your function gets smaller, in which direction? So you have a function like the one we just drew, e to the x, e to the 2y. And this guy grows the smallest when v is equal to -1, 2 divided by square root 5. When you're going in the negative direction, this guy goes to 0, right? When they both are negative. Is that okay? Zoom people, you have a question? Let me know. So this is your function, and if you want to find so gradient of f going in this direction down, then that's where your parabola grows. And minus gradient of f points towards the minimizer. So minus gradient of f is very interesting because it takes you to the minimizer, which is the origin. So this is the heart of gradient descent. You're following the direction of minus the gradient, which you can compute at every point. You compute it. It was 1, 2, so you put a minus. So you have -1, 2. It takes you to the origin. I mean, okay, it takes you there. Is that okay? Yeah, I'll do it here. I mean, I know this function. So this function here is so f of x y. This guy is x squared plus y squared. Okay, so that's the function. And then gradient of f is what? What's the first derivative? Yeah. So then, I don't know, let's say at 1, 1. This is equal to 2, 2. So then minus of gradient of f1, 1 is equal to -2, 2. So if you're over here at 1, 1, then you want to move in this direction, to the negative, to the -1, 1. Is that okay? So you can see another interesting thing we will talk about, that your algorithm can overshoot. This guy doesn't tell you go to 0, 0, tells you go to -1, 1. So when we go into Newton's method, we will have to catch ourselves from going too far to the away from zero. So once I compute the gradient here, it will tell me to go down to positive, right? Because gradient of f at -1 is equal to -2. So minus gradient of f -1 is 2. So the guy from here tells me to move in the opposite direction. Does that make sense? So we will come back to this. This is the heart of Newton's method. Oh, no, there's no acceleration here. No, Newton was a big guy. Like he did many things. Yeah. I don't know if you remember finding roots. So yeah, finding roots. The way you do it, you use Newton's method. Yeah, and I will give you the MATLAB code for that. Question by Zoom? Let's ask you questions. All right. So yeah, that's why this is the heart of this course. Gradient points to the greatest increase and minus gradient to the greatest decrease. All right. Another amazing fact is that it's normal, namely orthogonal, to level sets. So what's a level set? These are the places where your function is constant. So going back to our example, f of x equal to x squared plus y squared. And if you set this equal to a constant, say 1, can you tell me which points pictorially, what is it, the level set? Yeah, so how do you explain it? So we have this parabola, and if you go on the unit circle, x squared plus y squared plus equal 1, this guy gets mapped to the value 1. It has height 1. Is that okay? Okay. Right. So let's prove now that the gradient is orthonormal to the level sets. So, namely that gradient of f of x will be orthogonal to circles. Going back to our example. All right. So that's how you do it. Give me a curve inside the level set. So suppose this is the level set, the unit circle, and give me a curve inside it, RT. Okay, so this is a curve inside the level set. By definition, the derivative of this curve is called the tangent vector. Have you seen tangent vectors? You've seen it? Okay, good. So you have your level set and you have your curve R, and if you take its derivative, it gives you the tangent vector. So this vector here is called tangent to LC at RT. Okay, so this is RT. Okay. Yeah, it has to be inside. Yeah, like maybe I should use a different like, I don't know, like R1 or dr t at t equal 1, and you have your R1 over here. Let's say it's 0, okay? And then this vector over here will be the tangent. Okay. Yes. Well, yeah, we're working in 2 dimensions, but once you go higher, level sets are surfaces. So this is like the easiest, which do I have a, it's hard to visualize because we're not in high dimensions, but pretend that this surface, that if you give me any point x, y, z from here, pretend that f of x, y, z is equal to 1, okay? This is L of 1, okay? Then what we're saying is give me a curve RT inside the surface. Then if you want now tangent plane, you compute the derivative. So yeah, tangent vector is fine. Let me just talk about tangent vector. So tangent vector along the curve RT, it will just be the derivative at this point. Is that okay? Are you okay? So yeah, I can go slow here because we will come back to this. This notion of tangent vector, because in gradient descent, that's all you're doing. Each time you compute the tangent vector that tells you how to move. Yeah, so we'll come back to this. This is very important. Okay. All right, so this is called the tangent vector. And it has the amazing property that I'm going to show now. So like we said, right, RT is inside the level set. So f of RT is constant, okay? Because RT is inside the level set. Okay. So let's go step by step. So you have this, then you take the derivative of both sides. So I'll do it here on the side again. So dt of FRT and dct, which is 0 because c is constant. Okay, so that's how I get the first line. The second line is called chain rule or total derivative. Okay, so here we take derivative of f, and then the t derivative of the first coordinate of r, which is x1. What's a good example? Yeah, like suppose your f is x squared plus y squared, then f of rt is x1 squared t, x2 squared t. Yes, absolutely, yes. And then when I take t derivative, I get the first derivative of f times 2x1, right? X dot 1t, and yeah. Like that. Yep. All right. So yeah, let me clean this up. So when you take derivative, you end up with this. Question, Zoom? All right. So what's the point of this trick? I have it here, yeah. This guy is nothing else but the dot product of our gradient with this tangent vector. So this one says that 0 is equal to gradient when you dot it with a tangent vector. So that means that gradient is normal to the surface. So you give me some level set, the gradient will always point up. So it will be orthonormal, too much linear. So it will be orthogonal. All right. So let's do an example. I will use this formula to find the tangent plane for this surface. So this is a surface, and we set it to, this is the level set of a function. So can you tell me for which function this is the level set? I know it's easier, it's this one here. Oh, you're trying to, no, okay, this course is it's a bird course, so we're not asking, yeah, so this is the function. And so we're looking at L0. So X, Y, Z, so that F is 0. Okay. So yeah, I mean, we might be sneaky, right? We might give it to you in different versions. We might write it like this, or like this. Okay, and you have to like separate. Yeah. So okay, now that you have F, compute the gradient. Okay. So what's the gradient of this guy? Right, and if you plug in this vector, yeah, it gives you, so how do we do it? So this was 2x, 2y, 2z, and I plug in 2 times 0.6, 2 times 0.8, and minus 2, 1, and you get this. Okay? Is that okay? All right, so how do you find the tangent plane? The tangent plane, by definition, is given by all the vectors, v minus whatever the tangent reference point is. So you have to give me a, how do you call it? You have to give me a location in the surface. So yeah. So W minus V. So let me draw the picture. This is V, and I'm asking for the tangent plane at V. So center at V, and the way you find it is you solve this equation equaling 0. Is that okay? And the reason you put minus V is because you want it to be centered at V. Think of it as your origin. And you want to, starting from that V, you want to find the vectors that are inside the tangent plane. Not every vector is inside the tangent plane, right? So let me draw some stupid pictures. Here's V. Here's the tangent line. This guy is not a tangent vector. This guy is not a tangent vector. This guy is not a tangent vector. these two are. So it's not easy to find them. There's a lot of bad choices. Right? Is that okay? All right, so then, yeah, from what we just proved, you compute me the gradient, we did that over here, and then we dot it. So we dot this guy with this system, and it gives us this equation over here. Okay, so this is an equation, it's a linear equation, linear in x, y, z, and it will give you the following picture. So this is the function, and this plane is parameterized by this. Okay. So it gives you the tangent plane.
Sorry, Prof.
Yes, it is.
Yeah, sorry, I'm not sure if I'm getting this right, but I think there should be a negative sign in the z component for the gradient.
Oh, yeah, there is one. Yes.
Yeah.
Yes. Yeah, thank you.
Okay, thank you.
The computation is right. The minus one is not right. Yeah. All right. So this is minus. Yes. Good. And yeah, the gradient goes, oh yeah, it's 8. Good. So perfect. Tomorrow we'll continue with Thursday. Thank you. Yes. Oh, that's really, yeah. Is it hard? Let's see. Yes, that's me. Yeah. Yeah, just, okay. Yeah. I mean, if you get stuck, just come on Piazza. Okay, bye.